In 1173, builders in Pisa dropped a 14,500-ton stone foundation into mud, and the tower started sinking before the third floor was done. 800 years later, it still leans. Across the planet, a dam in China holds so much water, it literally slows the rotation of the Earth by 0.06 microseconds every single day. These are not flukes. They are not accidents. They are patterns, structures so extreme that the engineers who study them cannot fully explain how they survive. The answers are stranger than the questions, and the questions are about to get much darker. Dancing House, Prague. 99 concrete panels. Not a single one is the same shape. That is what it took to build a building designed to look like it is dancing in the middle of a European capital. Architect Frank Gehry and Vlado Milunic finished this structure in 1996 on the banks of the Vltava River. Every window frame is deliberately placed at an angle. None line up vertically. The goal was to make the entire facade appear to twist and sway, like two dancers mid-step. For structural engineers, this is a nightmare on paper. Load distribution in a wall full of irregular openings has no simple formula. Each of the 99 panels had to be individually calculated as its own geometry problem. No mass production, no shortcuts. Every single piece was custom poured and fitted by hand. The construction crews in Prague had to treat each section like a sculpture, not a building component. Stand across the river on a gray afternoon and watch the light hit it. The curves catch shadow in places straight buildings never could. The waist of the structure pinches inward, creating the illusion of a body bending. Your eyes keep moving because there is no flat surface to rest on. The whole building refuses to let you look away. When it was proposed, locals hated it. They called it an insult to Prague's Gothic skyline. Today, it is one of the most photographed buildings in the Czech Republic and houses offices, a restaurant, and a gallery. The engineers who built it said the hardest part was not the math. It was trusting that something this irregular could stand at all. And yet, it has stood for 3 decades now, without a single structural issue. If a building shaped like a dancer can survive, imagine what happens when engineers decide to make a bridge curl up like a living creature. If this is your first time hearing about a building, with 99 unique panels and 0 repeating shapes, you are exactly who this channel was built for. Subscribe to explore dangers so you never miss what comes next. Rolling Bridge, London. Most bridges exist to stay perfectly still. This one in London's Paddington Basin was designed to roll into a ball. Engineer Thomas Heatherwick built a 12-meter pedestrian bridge in 2004 that does not split in half or lift from one end to let boats pass. Instead, it curls. The entire structure folds inward, section by section, until both ends meet and form a perfect octagon on one side of the canal. The mechanism uses hydraulic rams hidden inside the steel and timber handrails. Each of the bridge's 8 sections is hinged to the next. When activated, the rams push fluid through the joints in sequence. The bridge slowly rolls like a caterpillar, pulling its body into a circle. The whole process takes about 3 minutes. Watch it happen in person, and your brain fights itself. The steel looks rigid. The timber looks heavy. Nothing about the structure suggests it can move. Then it begins to curve, and the geometry changes with each second. The straight walkway you were standing on moments ago is now an art installation sitting on the bank. What most people do not realize is that this bridge works on a single button. One press, the entire sequence runs automatically. Inside, the engineering is a dense web of precisely calibrated hydraulic pressure, joint tolerances, and load calculations that shift in real time as the bridge changes shape. Outside, it looks effortless. Heatherwick's team spent years testing the concept with physical models before a single piece of steel was cut. The risk was real. One miscalculated joint angle, and the bridge could jam mid-curl, stuck between open and closed with no manual override. That never happened. The bridge still rolls flawlessly, more than 20 years after it was installed. Simple on the surface, ruthlessly complex underneath. Now, imagine that same principle applied to water. A bridge built not over a river, but under one. Veluwemeer Aqueduct, Netherlands. A yacht floats directly over your car. You are not dreaming. You are driving through the Veluwemeer Aqueduct in the Netherlands, and the water is above your head. Built in 2002, this structure flips the entire concept of a bridge upside down. Instead of carrying cars over water, it carries water over cars. The road runs underneath a 19-meter-wide channel that connects the mainland to the island of Flevoland. Engineers used 22,000 cubic meters of concrete and drove steel piles deep into the lakebed to create a watertight trough suspended above the highway. The channel holds enough water for commercial boats and recreational yachts to cross without slowing down. Below them, vehicles pass through at highway speed, with no traffic lights, no waiting, and no delays. Drive through the underpass and look up through your windshield. The water surface is right there, separated from you by reinforced concrete and engineering precision. Sunlight filters down through the shallow channel and creates rippling patterns on the road surface. It feels like driving through an aquarium. Your brain tells you something is wrong. Water should not be above a highway. But there it is. The Dutch built this because the alternative was worse. A traditional bridge would have required boats to wait or cars to stop. Either solution meant bottlenecks on a critical transportation link. So they invented a third option that nobody had tried at this scale. The structure handles 28,000 vehicles per day underneath and hundreds of boats above simultaneously. The construction cost was lower than a conventional drawbridge. Maintenance is simpler. Traffic flow is uninterrupted in both directions for both modes of transport. Sometimes the most radical engineering solution is also the most practical one. The Dutch have a talent for making the impossible look obvious. If you had to pick between driving underwater or sailing over a highway, which side of this structure would you choose? Drop your answer in the comments below. The Interlace, Singapore. 31 apartment blocks. Each one is 70 meters long and 6 stories tall. Instead of standing upright like every other building in Singapore, they are stacked on top of each other, sideways. The Interlace, completed in 2013, looks like a giant game of Jenga, built by an architect who threw out every rule in the book. The blocks are arranged in a hexagonal grid and rotated 120 degrees from each other at every layer. This creates a stacking pattern that leaves enormous open spaces between the buildings. Those gaps become 8 massive sky gardens, connected terraces, courtyards, and green spaces suspended in the air. It is a vertical village turned horizontal. Stand at the base and look up. The building looms over you in all directions, but it does not feel oppressive. Light pours through the gaps between blocks. Wind moves freely through the open corridors in ways that sealed tower buildings never allow. In humid Singapore, where temperatures routinely hit 31 degrees Celsius, residents of the Interlace report noticeably cooler conditions than people living in conventional high-rises nearby. The structural engineering required to make this work is staggering. Each 70-meter block must transfer its load not straight down, but at angles through offset connection points to the blocks below. Architect Ole Sheeran and his team ran thousands of simulations to ensure that the rotated stacking pattern could handle wind loads, seismic activity, and the sheer weight of 31 massive concrete structures leaning on each other. Over 2,400 residents call it home. They chose it not because it was safe or conventional. They chose it because it reimagined what an apartment complex could be. The building won the World Building of the Year award in 2015. When structures start bending the rules this far, the results can be breathtaking. But the next construction bent the rules of gravity itself at a height that makes your palms sweat. That award-winning design is exactly the kind of story most channels skip over. If you want engineering pushed to its limits, a like on this video tells us to keep going deeper. Millau Viaduct, France. The tallest bridge structure on Earth stands 343 meters above the Tarn Valley in southern France. That is 19 meters taller than the Eiffel Tower. When the Millau Viaduct opened in December 2004, it shattered every record for structural height in bridge engineering. It held the title of the world's tallest bridge for over 20 years. The bridge stretches 2,460 meters across the valley, supported by 7 slender pylons that rise from the valley floor like the masts of an enormous ship. Each pylon tapers as it climbs, creating a silhouette so graceful that many engineers call it the most beautiful bridge ever built. But beauty was not the point. Speed was. Before the viaduct, drivers crossing this valley faced hours of congestion through the town of Millau. Now they cross in under 2 minutes. The construction method was as extreme as the structure. Engineers did not build the steel deck from the top down. They assembled the entire 36,000-ton deck on flat ground at both ends of the valley. Then, using synchronized hydraulic jacks, they pushed each massive section out over open air, advancing just 600 millimeters at a time. One wrong calculation, and the steel deck would have buckled under its own weight, collapsing into the valley below. Drive across it on a clear day, and the experience is surreal. The road surface feels like any other highway. But glance to the side, and the ground is over 270 meters below. Clouds sometimes drift beneath you. The pylons disappear into mist. You are driving through the sky on a road that should not exist at this altitude. Over 6 million vehicles cross the Millau Viaduct every year. Each driver trusts their life to a bridge that was pushed out over a canyon, 600 millimeters at a time. But what happens when engineers build not with steel and concrete, but with air bubbles? Eden Project, UK. The domes look like giant soap bubbles sitting in a crater. That is not an accident. The Eden Project in Cornwall, England, was built inside an abandoned clay mine, a pit so unstable that traditional glass structures would have collapsed under their own weight. So, engineers made the most counterintuitive decision in modern architecture. They built the largest greenhouses on Earth out of inflated plastic pillows. The material is ETFE, ethylene tetrafluoroethylene. It is 99% lighter than glass. Each panel is not a solid sheet, but an inflatable cushion, pumped full of air to maintain its shape. The result is a dome that can span 55 meters across the largest biome while weighing almost nothing. A single ETFE pillow can support the weight of a car driving over it, despite being thin enough to see through. Step inside the tropical biome, and the temperature hits you immediately. It holds a steady 35 degrees Celsius, with near total humidity. The dome contains over 1,000 plant species from tropical rainforests around the world. The air is thick and wet. Condensation drips from the hexagonal pillow structure overhead. You are standing in a manufactured jungle inside a hole in the ground in England. The engineering team, led by Nicholas Grimshaw, faced a site that no traditional builder would have touched. The clay walls of the old mine were still shifting. The ground was uneven and unreliable. Pouring a heavy foundation was out of the question. So the ETFE pillows gave them the impossible. Massive enclosed space with almost zero structural weight pressing into the unstable ground. Since opening in 2001, the Eden Project has attracted over 22 million visitors. Each one walks beneath a roof made of air, supported by nothing heavier than breath itself. Not every engineering miracle was designed to work perfectly. Some started as total failures and became legends anyway. Most channels would never explain how a building made of air bubbles holds up a truck. If this level of detail is what you look for, subscribing to Explore Danger means you will always find it here. Leaning Tower of Pisa, Italy. The tower was already sinking before the builders reached the third floor. In 1173, architects placed 14,500 tons of marble and stone onto a foundation just 3 meters deep. Beneath it sat a soup of clay, mud, and river sand, the worst possible base for a structure this heavy. By 1178, the south side had sunk measurably lower than the north. The lean had begun, and it would never stop on its own. Construction halted for nearly a century due to wars. When builders returned, they faced a choice that no modern engineer would make. They kept building. Rather than tear it down and start fresh, Italian craftsmen added floors with slightly taller columns on the sinking side, trying to compensate for the tilt by curving the structure upward. The result is a tower that is not only leaning, it is subtly banana-shaped. Stand at the base on the south side, and the tilt is visceral. The 56-meter tower leans at about 4 degrees from vertical. That sounds small until you look straight up and see thousands of tons of stone hanging over your head at an angle. Your body instinctively wants to step back. The shadow it casts on the ground is visibly wrong, elongated and shifted, like something out of a fever dream. By 1990, the lean had reached 5.5 degrees, and engineers feared imminent collapse. A massive stabilization project removed 38 cubic meters of soil from beneath the north side over 11 years, gently pulling the tower back to a safer angle. It worked. The tower lost about 45 centimeters of lean, without anyone touching the structure itself. Today, 3 million tourists visit each year. They stand beneath a building that engineers tried to save and nature tried to pull down for over 800 years. Neither side has fully won yet. If you think a leaning tower is hard to stabilize, wait until you see what American engineers did with a structure that leans at 45 degrees. On purpose. Gateway Arch, St. Louis. There is a 2.5-foot gap at the top of the tallest monument in the United States. To close it, Engineers had to pry it open to 8.5 feet using hydraulic jacks. That is how the 630-foot Gateway Arch in St. Louis was completed in 1965, by forcing the two legs of an inverted catenary curve apart and wedging a keystone section into the opening, while the entire structure flexed under thousands of tons of tension. Architect Eero Saarinen chose a weighted catenary curve instead of a simple circular arch. A catenary is the natural shape a chain takes when it hangs under its own weight. Flip it upside down, and every force flows through compression. Almost no bending stress at all. The arch essentially holds itself up, without a single internal support frame. It is 630 feet tall, 630 feet wide at the base, and its skin is stainless steel over reinforced concrete. Stand beneath it and tilt your head back. The legs rise impossibly narrow. Each triangular cross-section is 54 feet at the base, but only 17 feet at the top. The steel gleams against the Missouri sky. On windy days, the top of the arch sways up to 18 inches. You cannot see it from the ground. But if you are inside the observation deck at the peak, you can feel it. Dig-Bowser designed a transport system inside the arch, unlike anything else on Earth. Capsule pods ride on curved rails, rotating and tilting at every angle change to keep the passenger platform perfectly horizontal. You are carried up through the leg of a leaning steel curve in a pod that self-corrects its orientation in real time. This system has operated flawlessly for over 60 years. More than 4 million people ride those capsules every year, trusting a transport system inside a monument that flexes in the wind. Now imagine a structure that deliberately leans even more than the Gateway Arch, at an angle that makes engineers question everything. Montreal Tower, Canada. The Leaning Tower of Pisa tilts at 4 degrees. Montreal's Olympic Tower tilts at 45. That is not a typo. At 165 meters tall and a full 45-degree angle of inclination, the Montreal Tower is the tallest inclined structure in the world. It was completed in 1987, over a decade after the 1976 Olympics. It was designed to serve, and its geometry still makes structural engineers uncomfortable. The problem with the 45-degree lean is center of gravity. At this angle, the tower's mass shifts dramatically outward from its base. Every gust of wind, every temperature change that causes the steel and concrete to expand or contract, pushes the structure closer to its tipping threshold. Engineers compensated with a massive foundation and a structural design that channels the gravitational forces through a precisely calculated curve rather than a straight lean. Stand in the Olympic Stadium below and look up. The tower looms overhead at an angle that looks wrong. Your brain expects it to fall. The concrete surface is smooth and pale, and the curve of the structure sweeps upward and outward like something reaching for the sky and changing its mind halfway there. On overcast days, the top disappears into low clouds, and you lose all sense of how far the lean extends. 26 enormous steel cables drop from the tower's peak to the roof of the stadium below. These cables support the retractable dome, a roof system that can open and close over the entire stadium. The tower is not just an observation deck. It is the anchor point for a roof, covering 20,000 square meters of open space. Remove the tower, and the stadium loses its roof entirely. Over 300,000 visitors ride to the top each year. In a glass-enclosed funicular, they lean back at 45 degrees and trust that gravity will not win today. A structure leaning at 45 degrees is bold, but what about a building that has been under construction for over 140 years and still is not finished? You just learned about a tower that leans 5 times more than Pisa. If that number caught your attention, a like on this video helps us bring you more engineering pushed to the absolute limit. Sagrada Familia, Barcelona. Antoni Gaudí started building the Sagrada Familia in 1882. He died in 1926. The basilica is still not finished. For over 140 years, this church in Barcelona has been under continuous construction, the longest active building project in modern history. Current engineers estimate completion around 2026, though that date has shifted multiple times. Before computers existed, Gaudí needed to calculate the natural curves of his soaring arches. His solution was a handmade analog computer. He hung ropes from the ceiling of his workshop with small sandbags attached at precise intervals. Gravity pulled the ropes into catenary curves, the same natural shape that distributes weight most efficiently. Then he placed mirrors underneath and looked at the reflection. The upside-down ropes became right-side-up arches. He designed an entire cathedral using string and gravity. Step inside today and look up. The columns branch like trees, splitting into smaller supports as they rise toward the vaulted ceiling. Light pours through stained glass windows that shift from warm gold on the west side to cool blue on the east. The interior feels like standing inside a stone forest at sunrise. The ceiling is 45 meters above the nave floor. Every surface curves. Nothing is flat. Nothing is straight. The structural genius is hidden inside those curves. Gaudí's rope models calculated load paths so precisely that the stone columns carry enormous weight with minimal material. The vaulted ceilings look delicate, but are engineered to distribute thousands of tons of stone across branching support networks. Modern computer analysis has confirmed that Gaudí's analog calculations were accurate to within fractions of a degree. Over 4.5 million people visit annually. They walk through a building designed with rope and sandbags that modern software can barely improve upon. When one man's vision takes 140 years to build, you start to understand what ambition really means. But the next structure was built in just 4 years, across one of the most violent stretches of water on Earth. Golden Gate Bridge, USA. Currents in the Golden Gate Strait reach speeds of 100 kilometers per hour. Visibility drops to 0 in the fog. Eddies can capsize boats without warning. This is where engineers decided to build a suspension bridge in 1933, across a channel that had defeated every previous attempt to span it. The main span stretches 1,280 meters between two towers that rise 227 meters above the water. When completed in 1937, it was the longest suspension bridge in the world. Building it required braiding 129,000 kilometers of steel wire into two main cables at heights above 200 meters, often in blinding fog and gale-force winds. Workers pulled individual wire strands back and forth between the two towers using a massive pulley system. One strand at a time, thousands of passes. Chief Engineer Joseph Strauss insisted on a safety net beneath the bridge deck during construction, a radical decision for the 1930s. That net saved 19 men who fell during the build. They became known as the Halfway to Hell Club. 11 others died when a scaffold collapsed and tore through the net in 1937, just months before completion. Drive across it today, and the international orange towers rise above you like cathedral pillars. The cables hum in the wind. Below, the Pacific crashes against the strait's rocky edges. On clear days, you can see Alcatraz to the east and the Marin Headlands to the north. On foggy days, you drive into a white wall and the towers vanish above you. The bridge sways gently. It is designed to move up to 8 meters laterally. In extreme wind, over 40 million vehicles cross it every year. Each one rides on steel wire that was braided by hand 200 meters above water that would kill anyone who fell into it. The Golden Gate conquered violent water, but the next American project conquered something even more dangerous. A river powerful enough to carve the Grand Canyon. If you have ever driven across the Golden Gate and felt that sway in the wind, you know this is real. Share your experience in the comments. This community values people who have actually been there. Hoover Dam, USA. Pour 4.4 million cubic meters of concrete in a single block, and it would take 125 years to cool. That is the volume of concrete inside Hoover Dam. When construction began in 1931, engineers faced a heat problem that had never existed at this scale. Concrete generates enormous heat as it cures. A block this large would still be warm inside today if they had poured it all at once. The solution was brilliantly simple and brutally labor-intensive. Workers embedded 582 miles of 1-inch steel tubing throughout the concrete. Then, they pumped ice-cold water through those tubes continuously. The cooling system turned a 125-year problem into a 2-month problem. Each concrete block cured in about 60 days, instead of decades. Stand at the base in Black Canyon and look up. The dam wall rises 221 meters above the Colorado River. The concrete face is smooth and pale, curving gently between the dark canyon walls. The scale is disorienting. Your eyes cannot process the height because there is nothing familiar to compare it to. It feels less like a wall and more like the side of a mountain that someone poured. Building it killed 96 workers officially. Hundreds more suffered heat stroke in temperatures that hit 49 degrees Celsius in the canyon. Workers called the canyon floor the Inferno. They poured concrete around the clock in rotating shifts because the project could not afford delays. The entire dam was finished in 1936, 2 years ahead of schedule. Hoover Dam generates over 4 billion kilowatt hours of electricity annually, serving nearly 1.3 million people across Nevada, Arizona, and California. Every kilowatt passes through turbines spun by water, held back by concrete that was cooled through 582 miles of pipe. The dam tamed a river, but the next structure on this list uses a hole in a lake to tame a flood, and it looks like a portal to another dimension. 96 workers died building this dam in canyon heat that hit 49 degrees Celsius. Stories like this deserve to be told carefully. If you believe that too, a like lets us know to keep telling them with the respect they demand. Morning Glory Spillway, USA. A 22-meter-wide hole in the middle of a lake. It looks like someone pulled the drain plug on the entire reservoir. But this is not a whirlpool. It is the Morning Glory Spillway at Lake Berryessa in Northern California. And it is one of the most precisely engineered flood control structures in the United States. The spillway is a concrete funnel, a giant bell-shaped opening that sits flush with the lake surface. When water levels rise above a specific threshold, the excess pours over the lip and drops into a vertical shaft 61 meters deep. At the bottom, the shaft bends horizontally and channels the water through a 700-foot tunnel that empties into Puta Creek behind Monticello Dam. Visit during a wet year, and the sight is hypnotic. Water rushes over the rim in a smooth, circular curtain. The center of the funnel is a dark void. You cannot see the bottom. The sound is a low, constant roar that vibrates through the ground beneath your feet. Mist rises from the opening like steam from a giant vent. The U.S. Bureau of Reclamation built this spillway in the 1950s as part of the Monticello Dam project. The dam created Lake Berryessa by flooding an entire valley, including the town of Monticello. The spillway exists because, without it, heavy rains would push the lake over the dam and potentially cause a catastrophic breach. This hole in the water protects thousands of people living downstream. During dry years, the spillway sits exposed, a concrete throat rising from the lake bed, looking alien and out of place. Birds sometimes nest inside it. Locals call it the Glory Hole. It processes up to 48,400 cubic feet of water per second when fully active. From a hole that swallows floods, we move to an entirely different kind of engineering ambition, a country that built itself new land from the bottom of the ocean. Palm Jumeirah and the World Islands, Dubai. 7 billion cubic meters of sand. That is how much material engineers dredged from the Persian Gulf to build Palm Jumeirah, an artificial island shaped like a palm tree, visible from space. No concrete foundation, no steel skeleton, just sand and rock, compacted with vibration technology until it became solid enough to hold hotels, villas, and a monorail. Construction began in 2001 using a technique called rainbowing. Ships sprayed sand in controlled arcs to build up the island's shape layer by layer. To achieve the perfect palm leaf pattern visible from orbit, engineers used GPS satellite navigation, originally developed for military applications. Each sand-dumping ship followed coordinates, accurate to within centimeters. Without that precision, the palm fronds would have been shapeless mounds. Fly over it, and the geometry is startling. 16 fronds radiate from a central trunk, enclosed by a crescent-shaped breakwater 11 kilometers long. The breakwater alone required 7 million tons of rock. From the ground, you would never know. You are standing on manufactured land. The streets feel normal. The buildings feel permanent. But beneath every surface is compacted ocean floor. The World Islands Project pushed even further. 300 artificial islands arranged to form a map of the world, sitting 4 kilometers offshore. But unlike Palm Jumeirah, many of the world islands remain undeveloped. Investors purchased islands representing countries. Then the 2008 financial crisis hit. Some islands have slowly eroded. The dream of a miniature world map in the ocean stalled mid-sentence. Palm Jumeirah alone is home to over 80,000 residents. They live on sand pulled from the sea floor and shaped by military satellites. Every high tide tests the breakwater. Every storm reminds them that their island exists because humans decided the ocean was not big enough. Sand became land, but the next structure took ambition even higher, literally higher than any building in human history. You are watching a channel that explains how military GPS built an island from ocean sand. Most creators skip those details. If you want the full story every time, subscribing to Explore Danger is the way to get it. Burj Khalifa, Dubai. At 828 meters, the Burj Khalifa is taller than any structure humans have ever built. Its tip reaches higher than the cruising altitude of some small aircraft. Completed in 2010, it redefined what was structurally possible. By solving a problem that had stopped every previous skyscraper from reaching this height: wind. The secret is the Y-shaped floor plan. Instead of a traditional square or circular core, engineers designed a hexagonal central core surrounded by 3 wing-shaped arms arranged in a Y formation. As wind hits the building, the stepped setbacks along its height break up vortex patterns that would otherwise create oscillation. The building confuses the wind. Different sections experience gusts at different moments, preventing the synchronized swaying that destroys tall structures. Stand at the base and tilt your head back. You cannot see the top. The building narrows in stages as it climbs, disappearing into the sky like a needle dissolving into atmosphere. On clear days, the upper floors catch sunlight while the base sits in shadow. Residents on the highest floors see the sun set twice, once from their window, then again by taking the elevator down to a lower floor, where the sun has already dipped below the horizon. The concrete pumping operation alone broke records. Builders pumped concrete to heights above 600 meters using specially designed ultra-high-performance mixes that could withstand the pressure of being forced through vertical pipes taller than most buildings. A single foundation mat used 45,000 cubic meters of concrete. Over 12,000 workers constructed the tower during peak activity. The building contains 57 elevators, including double-deck units that travel at 10 meters per second. It serves as offices, residences, a hotel, and an observation deck that draws 1.87 million visitors annually. Height was conquered. But the next structure conquered something more subtle: the behavior of light itself. Louvre Abu Dhabi, UAE. This is not a single building. It is an entire city of 55 separate structures floating on the Persian Gulf, sheltered beneath a dome that weighs 7,500 tons, yet appears to hover above the water. The Louvre Abu Dhabi, designed by Jean Nouvel and opened in 2017, is the most ambitious museum complex ever built over open sea. The dome spans 180 meters in diameter. It is constructed from 7,850 individual metal stars, arranged in 8 overlapping layers of increasing size. Each star is a unique shape. Together, they create a pattern so complex that when sunlight passes through, it fractures into thousands of individual beams. The interior fills with what Nouvel calls a rain of light, shifting spots and streaks that move across the walls and water throughout the day. Walk beneath it at noon, the temperature drops immediately. The dome filters 75% of the sunlight, creating shade that feels cool even in Abu Dhabi's extreme heat. Spots of light dance on the floor, like reflections off a pool. The sound of the Gulf lapping against the building's edges mixes with the quiet of gallery spaces. It feels like standing inside a reef where the ocean has been replaced by air. The dome appears unsupported. In reality, 4 massive pillars are hidden within the structure, each positioned to be invisible from any viewing angle on the ground. The engineering required to make 7,500 tons look weightless involved 3 years of structural modeling and stress testing. Wind loads, thermal expansion, salt corrosion from the Gulf, every variable was accounted for. Some critics have called the Louvre Abu Dhabi more visually stunning than any painting inside it. Over 2 million people have visited since opening. They walk through a structure where engineering learned to manipulate light itself. From a dome that plays with sunlight, we cross into waters so violent that engineers had to anchor a bridge with concrete blocks heavier than battleships. Imagine walking beneath 7,500 tons of floating steel and watching light rain through metal stars. If that image stopped you for even a moment, consider sharing this video with someone who appreciates the impossible. Akashi Kaikyo Bridge, Japan. Each main cable is 1.12 meters thick and contains 36,830 individual steel wires. If you unraveled a single cable and laid the wire end to end, it would stretch approximately 300,000 kilometers, enough to wrap around the Earth more than 7 times. The Akashi Kaikyo Bridge in Japan held the record for the world's longest suspension bridge span from 1998 to 2022. With 1,991 meters of open air between its 2 main towers. The bridge crosses the Akashi Strait, one of the busiest and most dangerous shipping lanes in the world. Currents are powerful. Typhoons are frequent. In 1955, 2 ferries sank in this strait, killing 168 people. That disaster accelerated the push to build a bridge that could replace the deadly ferry crossings. Construction began in 1988 and took 10 years. To anchor the cables, engineers sank giant caissons, hollow steel and concrete cylinders, to the seabed at depths of 40 to 60 meters. Each anchorage was then filled with 350,000 tons of concrete. One anchor alone weighs as much as a large warship. These anchors exist for a single purpose: to prevent the cables from pulling free under the combined tension of the bridge deck, wind loads, traffic, and seismic forces. Drive across it, and the 2 towers rise 283 meters above the water ahead of you. The span takes about 90 seconds to cross at highway speed. Below, container ships pass through the strait like toys. The bridge deck sways perceptibly in strong wind. It was designed to withstand winds of 286 kilometers per hour and earthquakes up to magnitude 8.5. During construction, the 1995 Kobe earthquake struck and shifted the 2 towers apart by a full meter. Engineers adjusted the design and completed the bridge without starting over. Nature moved the foundations, and the engineers simply recalculated. One earthquake moved a bridge's towers a full meter apart, and they finished building it anyway. That story alone earns your attention. A like on this video tells us you want more of these stories. Great Wall of China, over 21,000 kilometers long. That is enough to stretch from New York to Los Angeles and back more than 3 times. The Great Wall of China is not one wall. It is a network of walls, watchtowers, trenches, and fortifications built across 2,000 years by multiple dynasties, each adding their own sections across some of the most punishing terrain on the continent. No cranes, no trucks, no machines of any kind for most of its construction. Workers passed bricks hand to hand up mountain faces. They strapped stones to mules and goats to haul materials up slopes too steep for humans carrying loads. In the mountain sections, the wall climbs gradients so extreme that the stairs built into the walkway rise at nearly 70-degree angles. Walking the wall today in these sections feels more like climbing a ladder than walking a path. Stand on the Jinshanling section at dawn, and the wall snakes across ridge lines in both directions until it dissolves into morning haze. The stones beneath your feet have been worn smooth by millions of footsteps over centuries. Watchtowers rise every few hundred meters, each one built with slightly different dimensions depending on which dynasty constructed that particular stretch. The wind at elevation carries the smell of dry stone and wild grass. Historians estimate that over 1 million workers died during the various construction periods. Many were buried inside the wall itself. The mortar in some sections was made from rice flour mixed with calcium, an innovation that created bonds stronger than pure cement. Sections built with rice mortar over 600 years ago remain structurally intact today. The wall was never a single military project. It was a rolling act of defiance against geography, invasion, and time itself. Every modern engineering estimate concludes the same thing. Rebuilding it today with machines would still take decades and cost hundreds of billions of dollars. Some constructions push limits. Others simply refuse to acknowledge that limits exist. This wall belongs to the second category. It was built by people who looked at 21,000 kilometers of mountains and said, "We will cover every one." Every structure in this video started with a decision that looked impossible. A building made of 99 unique panels, a dam that shifts Earth's axis, a wall longer than the distance between 2 oceans. These are not monuments to recklessness. They are proof that human ambition, when aimed at the edge of what seems achievable, does not just reach the edge, it moves it further out. Sit with that for a moment. Of every place we covered today, which one stayed with you? Which one made you stop and think about what it took? The lives, the years, the nerve, to make something that extreme exist? That question does not have a wrong answer. It just has your answer. Leave it in the comments. And if Explore Danger showed you something today that changed how you see what humans are capable of building, subscribe. There is more coming, and it goes further than this.